Hello, and welcome back to the Sleepy Science channel. Before we begin tonight, a quiet little nod to our friends over at Sleepy History, where the past is always told gently and with care. If you have not visited them yet, they are well worth an evening of your time. But tonight, you are here. And tonight we are going somewhere a little different. Not backward through time, though time will certainly come up. Tonight, we are going to the edge of the water. There is a particular kind of stillness that exists at the ocean's edge in the early hours of the morning, long before the first swimmers arrive, long before the beach fills with noise and color and the smell of sunscreen. There is a moment when the shore belongs entirely to itself. The sand is smooth and cool and untouched. The horizon is a pale gray line where sky and sea have not quite decided where one ends and the other begins. And the water, steady and unhurried, moves in and out along the sand with a sound like the whole world breathing. That sound, that rhythm, that ancient and patient movement, that is what we are going to explore together tonight. We are going to talk about tides. Now, I know what you might be thinking. Tides are simple enough. The water comes in, the water goes out. You learnt it in school. It has something to do with the moon. And yes, that is all true. But tides are one of those subjects that rewards slowness. They reward the kind of attention you can only give something when the rest of the world has gone quiet and you have nowhere to be and nothing to do except let your thoughts move gently from one thing to the next, like water moving from rock to rock along a shore. Because behind the simple fact of the tide rising and falling is a story that reaches all the way back to the formation of the Earth itself. A story involving the moon and the sun and the deep interior of our planet. A story about forces so massive they bend the shape of the ocean, and yet so subtle that creatures no larger than a thumbnail have been reading those forces for millions of years just to know when it is safe to feed. So find your comfortable place. Let your shoulders fall. Let your breath settle into something easy and slow, and let the tide come in. We will begin at the very beginning. The tide is not caused by the ocean. It is caused by the moon. This is one of those facts that most of us have technically heard before, and yet it somehow never quite lands with the weight it deserves. We hear it, we nod, we picture something vague, and we move on. But if you sit with it for a moment, really sit with it, something remarkable begins to take shape. The moon is, on average, about 384,000 kilometers from the Earth. That is a distance so large that if you tried to drive there in a car, traveling at a comfortable highway speed without ever stopping, it would take you roughly 160 days to arrive. And that is just to get there. Space is not empty in the way we tend to imagine it. It is not a blank nothingness. It is filled with gravity, that invisible but relentless force that everything with mass exerts on everything else. And the moon has quite a lot of mass. Not as much as Earth, certainly. Earth is about 81 times more massive than the moon. But the moon is not small. It has enough mass that even from that extraordinary distance of 384,000 kilometers, its gravitational pull reaches all the way down to Earth's surface and tugs at the water in our oceans. This is the origin of the tide. The moon pulling, the ocean responding. But here is where it starts to get genuinely interesting, and where most explanations stop too soon. The ocean does not just pile up on the side of Earth facing the moon. It piles up on the far side too. At any given moment, there are two bulges of water on Earth, one pointing toward the moon, one pointing directly away from it. And because Earth rotates underneath those two bulges roughly once every 24 hours, most coastal places on Earth experience two high tides and two low tides each day. Why two bulges? Why does the water also pile up on the side facing away from the moon, where you would expect the moon's pull to be weakest? The answer has to do with the difference in how strongly gravity pulls on things at different distances. The water on the side of Earth, facing the moon, is closer to the moon, so the moon pulls on it more strongly than it pulls on Earth's solid center. The water is drawn toward the moon, rising up in a bulge. But the solid Earth itself is pulled toward the moon more strongly than the water on the far side, because the solid Earth is closer to the moon than that far water is. So the solid Earth gets tugged a little bit away from the far side water, and the far side water, being slightly left behind, forms its own bulge. A bulge caused not by being pulled toward the moon, but by the rest of the planet being pulled slightly away from it. 2 bulges, 2 high tides per day, and the quiet, persistent, invisible hand of the moon behind all of it. There is something deeply calming about this when you let it settle in. The fact that the ocean's most recognizable behavior, something people have watched and lived alongside for as long as people have existed, is caused by something 1/3 of a million kilometers away in space, doing nothing more than existing, doing nothing more than having mass, and letting gravity do what gravity does. The tide is not a local thing. It is a cosmic one. The moon is slowly moving away from Earth, and the tides are the reason why. Every year, the moon drifts approximately 3.8 centimeters farther from Earth. That is about the same rate at which your fingernails grow. It does not sound like much, and in human terms, it is not. In a single lifetime, the moon recedes by only about 3 meters. You would never notice. The tides would look and feel the same. But the Earth and the moon have been together for about 4.5 billion years. And over that span of time, those tiny centimeters add up to something extraordinary. The moon today is much farther from Earth than it was when it first formed. And it was much closer to Earth during the periods of deep prehistory when the first single-celled life was just beginning to find its footing in the shallow seas. When the moon was closer, the tides were dramatically stronger. Not slightly stronger, dramatically, ferociously stronger. The ocean sloshed and surged in ways that would be almost unrecognizable to us today. Tidal waves, not in the tsunami sense, but in the sense of the ordinary tidal range, the difference between high and low tide, were likely hundreds of meters tall, in some places, during the earliest epochs of Earth's history. And here is the mechanism behind the moon's slow retreat. It is the tides themselves that are pushing the moon away. The gravitational pull between the Earth and the moon is not perfectly symmetrical. As the moon pulls on Earth's oceans and creates the tidal bulge, Earth's rotation carries that bulge slightly ahead of the position directly below the moon, because Earth rotates faster than the moon orbits. The bulge ends up a little bit in front of the moon's current position, and because that bulge has mass, and mass has gravity, the bulge pulls on the moon in a forward direction, speeding it up slightly. When the moon speeds up, orbital mechanics takes over, and a faster-moving moon settles into a slightly higher, wider orbit. The moon moves outward. So every tide that rises and falls, every ordinary morning when the water creeps up the beach at your favorite coastal spot, is incrementally nudging the moon a tiny bit farther away. The ocean is slowly, patiently, grain by grain, centimeter by centimeter, pushing the moon away from Earth. This has been happening for 4.5 billion years. There is something almost melancholy about it, and yet something strangely peaceful too. The moon and Earth are in a slow, long conversation. The ocean is the messenger, and the message is delivered twice a day, every day, without fail. The sun also creates tides, and together with the moon, it produces the highest and lowest tides of all. The moon gets most of the credit for tides, and rightfully so. Even though the sun is vastly more massive than the moon, about 27 million times more massive, the sun is also vastly farther away. And when it comes to tidal forces, distance matters much more than mass. The Sun is about 150 million kilometers from Earth, compared to the Moon's 384,000 kilometers. Because of that enormous additional distance, the Sun's tidal effect on Earth's oceans is only about 46% as strong as the Moon's. But 46% is not nothing. When the Sun and the Moon align when they are pulling in the same direction, either because the Moon is between the Earth and the Sun during a new moon, or because the Earth is between the Sun and the Moon during a full moon, their tidal forces add together. The result is what sailors and coastal communities have always called a spring tide. Not spring as in the season, but spring from an old Germanic word meaning to rise up, to leap, to surge. During spring tides, high tides are noticeably higher than usual, and low tides are noticeably lower. The tidal range, that gap between the highest and lowest points of water in a given tidal cycle, stretches to its widest. And when the Moon is at a right angle to the Sun during the first and third quarters of the lunar cycle, when you see that perfect half moon in the sky, the tidal forces partially cancel each other out. The result is a neap tide. During neap tides, the range between high and low water is at its smallest. The tidal swing is modest, quiet, understated. So the rhythm of the tides is not a single simple beat. It is two rhythms woven together. The roughly twice daily rhythm of high and low tides driven by Earth's rotation, and the roughly monthly rhythm of stronger and weaker tides driven by the changing alignment of the Sun and Moon. Spring tides at new moon and full moon. Neap tides at the quarter moons in between. And within each cycle, a gradual waxing and waning of tidal force. It is, in a way, like music. The daily tide is the baseline rhythm, steady and regular. The monthly lunar cycle is the melody shifting above it. And occasionally, during a perigean spring tide, when the Moon is both aligned with the Sun and at its closest point in its elliptical orbit, the two rhythms hit a peak together, and the tides rise and fall in ways that can genuinely surprise even people who live by the water all their lives. Different coastlines experience tides in dramatically different ways. You might assume that tides are more or less the same everywhere, that the ocean is one connected body of water and the tidal forces act on it uniformly. But geography makes this gloriously complicated. The shape of coastlines, the depth of the water, the width of bays, the layout of channels and shelves, all of these things interact with the tidal forces in ways that create extraordinarily different tidal experiences from one place to the next. The Bay of Fundy, which sits between the Canadian provinces of Nova Scotia and New Brunswick on the Atlantic coast of Canada, is perhaps the most famous example in the world. Its shape is like a long funnel that narrows toward the northeast, and the length of the bay happens to be almost perfectly tuned to the rhythm of the tides, the way a wine glass can be made to ring at a particular frequency if you run a wet finger around its rim. Twice a day, the Atlantic tide pushes into this funnel. As the water gets funneled into a progressively smaller space, it has nowhere to go but up. The result is the highest tidal range on Earth. At the head of the Bay of Fundy, the difference between high tide and low tide can exceed 16 meters. 16 meters. That is the height of a 5-story building. At low tide, you can walk across the flat, wet seabed and look up at wooden boat hulls hanging above you, suspended on their anchor lines, resting against wharf pilings. 6 hours later, all of that seabed is gone, buried under meters of cold, rushing, greenish-brown Atlantic water. Boats that were sitting on mud are now floating freely. The transformation is total, and it happens every single day. People who live along the Bay of Fundy do not experience tides as a background fact of coastal life. They experience them as a central organizing force. The rhythm of the tides shapes when you can work on the boats, when you can dig for clams, when you can walk across certain paths and when those paths are underwater. Time itself along the Fundy shore is divided not just into morning, afternoon, and evening, but into the 4 stages of the tidal cycle. On the other end of the spectrum, some places in the world experience almost no tidal range at all. The Gulf of Mexico, in the southern United States, has a tidal range of less than 30 centimeters in many locations, so small that visitors from the Atlantic coast sometimes struggle to even notice a tide at all. The Mediterranean Sea, enclosed as it is by surrounding land with only a narrow connection to the Atlantic through the Strait of Gibraltar, has tides so subtle that the ancient Greeks and Romans who lived along its shores were largely unaware that other parts of the world had noticeable tides at all. When Julius Caesar's forces first arrived on the shores of Britain in around 55 years before the Common Era and encountered the dramatic tidal range of the English Channel, the Roman soldiers were reportedly astonished. They had almost no reference point for it. The ocean is one body of water, but tides are intensely local things, shaped by the land that holds the water as much as by the forces that move it. Some coastlines experience only 1 tide per day instead of 2. The twice-daily tidal pattern, 2 high tides, 2 low tides, each about 6 hours apart, is the most common pattern in the world, and it is what most people picture when they think of tides, but it is not universal. In some parts of the world, including the Gulf of Mexico and parts of Southeast Asia, the 2 daily tidal cycles become so unequal in height and timing that they effectively merge into a single, noticeable tidal event per day. 1 high tide dominates, 1 low tide follows, and the whole cycle repeats roughly once every 24 hours and 50 minutes. This is called a diurnal tide, from the Latin word for daily. The reason this happens is complex and has to do with the angle of the moon relative to Earth's equator. When the moon is positioned at a steep angle above or below the equator, the 2 tidal bulges it creates are not centered evenly on the equator, they are displaced. One bulge ends up in the northern hemisphere, the other in the southern hemisphere. For coastlines near the equator or at certain latitudes, this means that as Earth rotates, a given stretch of coast passes through one bulge quite prominently and barely grazes the other, experiencing 1 strong tide and 1 weak one. When the weak one becomes weak enough, it effectively disappears, and the coast is left with just 1 tide per day. This diurnal pattern creates its own particular rhythms and its own particular culture. The fishing communities along the Gulf Coast of the United States and Mexico have always organized their days differently from those on the Atlantic coast. The tide comes in, the tide goes out, and there is a long period of quiet in between, rather than the constant, twice-daily choreography of the Atlantic. The ocean, even in this most basic rhythm, refuses to be entirely simple. Life on Earth evolved to the rhythm of the tides, and that ancient beat is still written into living things today. Before there were forests, before there were insects or reptiles or birds, before there were fish with legs learning to haul themselves up onto dry land, before almost anything we would recognize as complex life, there were tidal zones, shallow margins of ocean where water came and went, where the chemistry of the sea mixed with the exposure of the air, where nutrients concentrated and conditions changed twice a day in ways that put enormous pressure on whatever was living there. The intertidal zone, that strip of coastline between the highest tide line and the lowest tide line, is one of the most demanding environments on Earth. Organisms living there must cope with being submerged in salt water for several hours, then exposed to open air, sunlight, wind, and sometimes crushing heat for the next several hours, then submerged again, over and over, day after day, year after year, across millions of generations. The creatures that succeed in that zone must be genuinely extraordinary, and they are. Consider the humble limpet. A limpet is a small marine snail, conical in shape, that clings to rocky surfaces in tidal zones around the world. When the tide is in, limpets move slowly across the rock, grazing on algae with a remarkable tongue-like structure covered in tiny teeth. When the tide begins to go out, limpets return to a specific spot on the rock, their home scar, and clamp down with a muscular foot that can generate enough suction to withstand a wave impact that would send a grown adult tumbling. They wait. They slow their metabolism. They seal themselves against the rock so tightly that they can hold a small reservoir of water inside their shell to survive the exposure. When the tide comes back in, they release, and the slow grazing begins again. Limpets can live for many years, and they know the rhythm of the tide so well that researchers have found they will begin preparing to clamp down before the tide actually retreats, anticipating the exposure, responding not just to the physical sensation of the water leaving, but to some internal sense of time that has been calibrated over millions of years of tidal evolution. The fiddler crab is another beautiful example. Male fiddler crabs are easily recognized by their single enormous claw, which they wave in elaborate displays during mating season. Fiddler crabs live in burrows in the mud of tidal flats, and they are active primarily at low tide, when they emerge to feed on the exposed mud and to engage in their social dramas. As the tide rises and the water approaches, they retreat to their burrows and seal themselves in. But fiddler crabs taken away from the coast and placed in a laboratory with constant light, constant temperature, and no visible tidal cues continue to show a 12.4-hour activity cycle for days or even weeks. The 12.4-hour rhythm, the interval between successive high tides, is so deeply embedded in their biology that it runs even when the environmental cues are removed. It is not just a behavioral pattern, it is built into their cells. This is true of many intertidal organisms. The biological clocks of coastal creatures are tuned not just to the 24-hour cycle of day and night, which all life on Earth shares, but also to the tidal cycle, a completely separate rhythm, running independently, calibrated to the moon. We tend to think of our internal body clocks in terms of the daily cycle of light and dark, the circadian rhythm. But intertidal life carries a second clock, a tidal clock, and has carried it for hundreds of millions of years. It is a reminder that the moon's influence on life goes deeper than the tide itself. The moon has shaped evolution. It has written its rhythm into genetics, into the nervous systems of creatures, into the very chemistry of life at the ocean's edge. The ocean is not the only thing the moon's gravity moves. The solid Earth bends with the tides too. This one surprises almost everyone. We think of solid rock as something fixed and rigid, something that does not bend or flex under ordinary circumstances. But the Earth is not perfectly rigid. Its interior is under enormous pressure, and its outer layers, though solid, have enough elasticity that the tidal forces of the moon can actually deform them. The surface of the solid Earth rises and falls with the tides. Not by as much as the ocean does. We are talking about a vertical movement of only about 20 to 30 centimeters in most locations, rising and falling twice a day as the tidal forces sweep across the planet. You cannot feel it. You will never notice it while standing on the ground. But it is real, and it is measurable with modern instruments. This phenomenon is called the solid Earth tide, or sometimes the body tide, to distinguish it from the ocean tide. GPS satellites are sensitive enough that they have to account for the solid Earth tide in their calculations. Without correction for it, GPS measurements would drift by enough to cause meaningful errors in precision surveying and navigation. There is also a phenomenon called the ocean loading effect. When the ocean tide piles water up on a coastline, the weight of all that additional water actually pushes the underlying crust down slightly. When the tide retreats and the weight is removed, the crust springs back up. The seabed is breathing with the tides, very slowly, very subtly, but measurably so. And even the atmosphere is not immune. The gravitational pull of the moon creates atmospheric tides, tiny pressure variations that sweep around the Earth twice a day in sync with the ocean tides. These atmospheric tides are much smaller in effect than ocean tides, but they are real. The air itself, in its way, is tugged by the moon. The whole Earth participates in the tidal rhythm. Rock, water, and air, all moved, all gently, persistently deformed by the gravity of the moon. The tide is not something that happens to the ocean. It is something that happens to Earth. Ancient civilizations built their lives around the tides and held them sacred. The tides were not always understood scientifically. For most of human history, they were experienced as something powerful and somewhat mysterious, something that clearly responded to the moon, but whose exact mechanism was not known. And in the absence of a full scientific explanation, the tides were woven into myth, religion, and the deep structure of daily life. The ancient Greeks were fascinated by tides but lived mostly along the nearly tideless Mediterranean, where the subject was mostly theoretical for them. When Alexander the Great sent his admiral Nearchus on a voyage along the coast of Persia and India in around 325 years before the Common Era, the fleet was nearly destroyed when it was caught on a flat, suddenly dry seabed at low tide, a tidal experience that the Mediterranean-bred sailors simply had not prepared for. Nearchus later described the event in terms of astonishment and terror. Pythias of Massalia, a Greek explorer from what is now Marseille in France, traveled north to the British Isles in approximately 320 years before the Common Era, and he was likely the first Greek scholar to observe and write about the dramatic tidal ranges of the Atlantic and the North Sea. He connected the tides explicitly to the moon, noting that the tides were strongest at new moon and full moon. His observations were so far outside the experience of his Mediterranean contemporaries that many of them dismissed him as a liar and a fantasist. The Norse peoples of Scandinavia, living among the dramatic tidal channels and fjords of the North Sea, had a particularly intimate relationship with tidal forces. Old Norse sagas reference tidal conditions in practical terms, noting when channels could and could not be navigated, when fishing grounds would be exposed, when particular crossings were safe. The tide was not background noise. It was a central character in the geography of life. In the cultures of the Pacific Islands, the tides were woven into navigation, agriculture, and ceremony. The Polynesian and Micronesian peoples who colonized the Pacific in great voyaging canoes over thousands of years read the ocean as a text, and the tides were part of that text. Tidal patterns along coastlines helped identify where land was even before it could be seen. The way the swell changed near a shore, the way tidal currents shifted, these were clues read by expert navigators who had no instruments other than their own senses and the accumulated knowledge of generations. In many Pacific cultures, the deep sea and the tides were understood as living forces with their own intelligence and agency. The Maori people of New Zealand described the tides as the breathing of a great ocean ancestor. The water pulling back was the inhalation. The water surging forward was the exhalation. The rhythm of the tides was the rhythm of life itself, expressed at the largest possible scale. There is wisdom in that image, even beyond its poetic beauty. The ocean is not a passive container for water. It is dynamic, living, breathing in its way. And the tide is not just a mechanical consequence of gravity. It is the ocean's most visible and most ancient behavior, older than any creature now living, older than the continents in their current shapes, older than almost anything we can name. The first person to correctly explain the tides was Isaac Newton, and he almost did not believe it himself. For most of recorded history, the connection between the moon and the tides was observed without being understood. People knew the moon was involved. They could see that spring tides happened at new moon and full moon. They could see that the tidal pattern followed the moon's position in the sky. But explaining the mechanism, explaining why and how the moon's gravity reached across space to move the ocean, required a new kind of mathematics and a new kind of thinking. That thinking arrived with Isaac Newton. Born in Lincolnshire, in England, in 1642, Newton published his landmark work, Principia Mathematica, in 1687. In it, he laid out the law of universal gravitation, the idea that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. And then he applied this law to the tides. Newton showed that the tidal force, the difference in gravitational pull across the diameter of the Earth, was exactly the right mechanism to explain the dual tidal bulges on Earth, the timing of spring and neap tides, and the relative contributions of the moon and the Sunday. His mathematical explanation matched the observed behavior of tides with a precision that had never been achieved before. But Newton was also honest about the limits of his own work. He could explain the astronomical forces driving the tides. He could not fully explain why different coastlines behaved so differently, why the Bay of Fundy had enormous tides while the Mediterranean had almost none. That required understanding how the ocean's geometry modified and amplified the tidal forces, and that problem was far more complex. Newton reportedly described his own work on gravitation with characteristic modesty, suggesting that he was like a child playing on the beach, who occasionally found a smoother pebble than usual, while the great ocean of truth lay all undiscovered before him. It is an image that feels particularly fitting when we are talking about the ocean and its tides. Even in explaining the tides, Newton gestured toward everything that was not yet understood. The tides have shaped the coastlines we see today and will go on shaping them. Water is patient. It does not hurry. It does not need to. Given enough time, water will accomplish things that seem impossible, carving canyons through solid rock, smoothing boulders into round pebbles, undercutting cliff faces until they tumble into the sea. And tidal water, returning twice a day without fail, year after year, century after century, has had extraordinary amounts of time to work on the coastlines of the world. The gentle sweep of tidal water across sandy beaches gradually sorts the sand by grain size, carrying smaller, lighter grains farther up the beach and leaving heavier grains lower. Tidal currents scour channels through estuaries, keeping them navigable. Tidal action deposits sediment in patterns that build tidal flats and salt marshes, those gentle, waving fields of grass that fringe so many coastlines and that are now recognized as among the most ecologically valuable ecosystems on Earth. Salt marshes are created almost entirely by the tides. They exist in that middle zone where the tide comes in regularly enough to bring salt water and sediment, but not so regularly that the land is permanently submerged. The grasses and plants that colonize that zone are remarkable. They can tolerate being drowned in salt water twice a day and then exposed to air, and they have evolved specialized tissues and salt gland mechanisms to manage the chemical stress. Their roots hold the sediment, their stems slow the water, and gradually the marsh builds itself upward, centimeter by centimeter, year by year. Salt marshes absorb storm surge, protecting inland areas from flooding during hurricanes and severe storms. They filter runoff from the land before it reaches the open ocean. They sequester carbon from the atmosphere at remarkable rates, and they provide nursery habitat for an enormous proportion of the commercially important fish and shellfish that humans harvest from the sea. The tides built these places. The tides maintain them. And where tides have been blocked or disrupted, where seawalls or development have changed the tidal flow, salt marshes have declined and sometimes disappeared entirely. The tides are not just interesting scientifically. They are load-bearing pillars of coastal ecosystems. Remove them or diminish them, and the whole coastal ecology shifts. There are ancient rocks that contain a record of the tides from more than 600 million years ago. One of the extraordinary things about tides is that they leave physical records, not in the obvious ways, like written accounts or artifacts, but in the geological record. Certain kinds of sedimentary rock form in tidal environments, and they preserve the signatures of the tides in patterns of layering that geologists have learned to read. Tidal rhythmites are the most dramatic example. These are finely layered sedimentary sequences formed in tidal flats and estuaries, where each high tide deposits a thin layer of sediment. As the tide waxes and wanes through the spring-neap cycle over roughly 2 weeks, the layers of sediment alternately thicken and thin in a rhythmic pattern. Each couplet of thicker and thinner layers represents one tidal cycle. Groups of layers can be counted to reveal the pattern of spring and neap tides, and from there, the number of tidal cycles per year can be estimated. Ancient tidal rhythmites have been found in places like the Elatina Formation in South Australia, deposited about 620 million years ago. Analysis of these ancient sediments suggests that at that time, the Moon was somewhat closer to Earth, and as a result, there were roughly 422 days in a year and roughly 13 lunar months. The Earth was rotating faster, and the Moon was completing more orbits per year. In other words, the rhythm of the tides 600 million years ago was different from what it is today. Other ancient rhythmites from different geological periods have confirmed this picture of a gradually slowing Earth and a gradually retreating Moon. The geological record of the tides is, in a sense, a record of the evolving relationship between the Earth and the Moon, a diary written in stone. There is something profoundly humbling about holding a piece of 600 million year old rock and realizing that the faint layering you can see in its face was put there by tides. Tides, driven by the same Moon that tonight is, pulling at the same ocean, just from a slightly different distance, at a slightly different rate, in a world that has changed almost beyond recognition in every other way, but not in this. The tide was here long before us. It will be here long after. Tidal bores are one of the ocean's most dramatic and least known phenomena. In most places, the tide arrives gradually. The water level rises smoothly over several hours, the sea creeping up the beach or into the estuary in the way you might pour water slowly into a bowl. But in a small number of places around the world, the tide does not arrive gradually. It arrives as a wave, a visible, rushing wall of water that moves up a river against the current, churning and roaring, sometimes reaching heights of several meters. This is a tidal bore, and it is as dramatic as it sounds. Tidal bores happen when the tidal range is large and when a bay or estuary narrows and shallows rapidly as you move inland, funneling the incoming tide and causing it to build up into a wave rather than a gradual rise. The conditions required are quite specific, which is why true tidal bores are relatively rare. There are only a few dozen significant ones in the world, but where they do occur, they are extraordinary. The Qiantang River in China, which flows into Hangzhou Bay, south of Shanghai, has what is generally considered the world's most powerful tidal bore. During the highest spring tides, the Qiantang bore can reach heights of up to 9 meters and travel at speeds of up to 40 kilometers per hour. The sound of its approach is described as a deep, sustained roar, audible from kilometers away, like distant thunder that grows and grows without stopping. Watching it approach from the riverbank, you see first a white line on the river. Then the line resolves into a churning, frothing wave face. And then the wave arrives, and the entire character of the river changes in moments, from a placid watercourse to a turbulent, moving wall of grey-brown water. The Qiantang bore has been observed and recorded in China for well over 2,000 years. There are accounts of it in documents from the Han Dynasty. descriptions of crowds gathering on the riverbanks to watch it pass. In the Tang dynasty, around 1,300 years ago, it was fashionable and daring to ride the boar on small boats, an activity that occasionally proved fatal and apparently made it more attractive to a certain type of young aristocrat. The Severn estuary in England also has a well-known tidal boar, though smaller than the Qiantang. The Severn boar travels up the river on certain spring tides and draws crowds who watch from the banks and, in recent decades, surf the wave on surfboards and kayaks. The Severn boar is a gentle, rolling wave by comparison with the Qiantang, but it can still be several meters high, and it carries enormous energy. The Amazon River in Brazil has a tidal boar called the pororoca, a word from the indigenous Tupi language, meaning great roar, that can reach heights of 4 meters and travel more than 800 kilometers up the river from the coast. The pororoca arrives twice a day during the highest spring tides and has traditionally been regarded with deep respect and some fear by communities living along the river. In recent decades, Brazilian surfers have ridden the pororoca for distances of several kilometers, which is both impressive and probably best attempted only by people who have fully thought through the risks. The tidal boar is the tide at its most dramatic. It is the gentle, patient ocean, choosing one particular geography and one particular moment to announce itself with something close to fury. The tides of other planets and moons are some of the most violent forces in the solar system. The tidal forces we experience on Earth are significant. They move the ocean, they slowly push the moon away, they bend the solid crust of the planet. But by the standards of what tidal forces can do elsewhere in the solar system, Earth's tides are modest. In other corners of our solar system, tidal forces create environments so extreme that they fundamentally transform entire worlds. The most dramatic example is Io, one of the 4 large moons of Jupiter, first identified by Galileo Galilei in 1610. Io is roughly the same size as Earth's moon, but it orbits Jupiter, a planet more than 300 times more massive than Earth, at close range. And it is in a special orbital relationship with 2 other large Jovian moons, Europa and Ganymede, that keeps its orbit slightly elliptical. As Io's distance from Jupiter changes along that elliptical orbit, the tidal force on Io changes too, squeezing and releasing the moon in a continuous gravitational grip. The result is extraordinary. Io is the most volcanically active body in the entire solar system. Its surface is covered in active volcanoes, some of which shoot plumes of sulfur hundreds of kilometers into space. The interior of Io is kept continuously molten by the relentless tidal flexing. The tidal forces of Jupiter literally heat the rock of Io from within, keeping it in a state of constant geological violence that would be inhospitable to any life as we know it. On the other end of the spectrum, Europa, another of Jupiter's large moons, is kept in a perpetual state of warm, liquid water beneath its icy surface by similar, but somewhat gentler, tidal heating. Europa's surface is covered in a thick shell of ice, but underneath that ice, tidal energy keeps the water liquid in a deep, dark global ocean. This ocean has no sunlight reaching it, but it has energy from tidal flexing, and it may have hydrothermal vents on the seafloor where that energy is released, in ways that could, some scientists believe, support life. The tides of Jupiter may have created the most promising environment for extraterrestrial life in our solar system, hidden beneath the ice of a moon 1 billion kilometers from Earth. Enceladus, a moon of Saturn, shows similar behavior on a smaller scale. Tidal heating from Saturn keeps part of Enceladus's interior liquid, and active geysers near its south pole shoot plumes of water, vapor, and ice particles out into space, an ocean venting through a crack in a moon's icy shell into the vacuum of space. The plumes of Enceladus have been sampled by spacecraft and found to contain organic molecules and hydrogen, both consistent with the kind of chemistry that could, in principle, support life. Tides are not just a feature of Earth, they are a fundamental force in the solar system, reshaping worlds, heating interiors, maintaining liquid oceans far from the sun where no sunlight could ever reach, and potentially creating the conditions for life in places we would never otherwise have thought to look. The humble tide that laps at the beach is the local manifestation of something vast, cosmic, and endlessly creative. The tidal zone is where scientists believe life may have first left the sea for the land. One of the oldest and most enduring questions in biology is how life made the transition from ocean to land. The ocean was life's original home. The first cells appeared in water, and for the vast majority of Earth's biological history, roughly 3.5 billion years out of 4 billion years of life, all life remained in the ocean. The transition of life to land is one of the pivotal events in the history of the planet, and it happened in stages over long periods of time, in places that were neither fully ocean nor fully land. The tidal zone was probably central to this story. Imagine, if you will, the coastlines of Earth roughly 400 million years ago. The continents were arranged very differently from today, and the shallow coastal seas were full of live fish of many kinds, including some with sturdy, lobed fins that they used to push themselves along the sea floor, and some that could breathe air to some degree when oxygen levels in stagnant water fell too low. The tidal zone along these ancient coasts was a place of opportunity and challenge, as it is today. An animal with the ability to tolerate brief exposure to air, to use its fins to haul itself up onto a surface, to find food in the tidal zone that other creatures could not reach. Such an animal would have been at a significant advantage. And natural selection, given enough generations and enough pressure, finds advantages. The transitional fossils linking fish to early tetrapods, the four-limbed ancestors of all land vertebrates, including us, have been found in what were clearly shallow coastal and estuarine environments. Tiktaalik, a famous transitional fossil, discovered in Canada in 2004 in rocks roughly 375 million years old, shows the mix of fish and early tetrapod features that you would expect in an animal living in tidal shallows: sturdy pectoral fins that could prop it up, a neck that could turn, eyes positioned on top of the head like an alligator rather than on the sides like a fish. The tidal zone did not create the transition to land that was accomplished by evolution over millions of years and through countless individual lives. But the tidal zone was the landscape where the transition happened, the environment that put pressure on ancestral fish in ways that rewarded the ability to cope with air and with firm substrates. The twice-daily rhythm of submersion and exposure that challenges life in the intertidal zone today was the same rhythm that, over unimaginable spans of time, helped shape the evolutionary path that eventually produced every land vertebrate alive today, including the one listening to this, lying somewhere comfortable and growing pleasantly sleepy. The tides have been shaping life for almost as long as there has been life to shape. Tide pools are entire worlds compressed into small spaces. If you have ever crouched at the edge of a rocky tidal pool and looked into it carefully, you have experienced something that scientists never quite stop finding wonderful: the sensation of discovering an entire miniature ecosystem tucked into a space you could cross in a few strides. Tide pools form where rocky coastlines hold water in their depressions and crevices as the tide retreats. The pool is a temporary refuge and also a temporary trap. Everything inside it is isolated from the open ocean for the hours between tides, cut off from the larger body of water that might otherwise moderate temperature, refresh oxygen, or dilute salt concentrations as evaporation does its slow work in the sun. The creatures living in tide pools have evolved to manage these extremes. Sea stars, often called starfish, though they are not fish, move through tide pools on hundreds of tiny tube feet, hunting mussels and barnacles. They are voracious predators, able to pry open bivalve shells and extend their stomachs out of their bodies and into the gap to digest the animal inside. Sea anemones anchor themselves to rock and wave their sticky tentacles through the water, trapping small crustaceans and fish fry. Hermit crabs drag their borrowed shells from crevice to crevice, scavenging. Periwinkle snails graze algae from every available surface. Tiny blennies and gobies hide under algal fronds and dart out to snatch prey. Each tide pool is also organized by height. The highest pools, reached only by the largest spring tides, are the harshest environments exposed for the longest periods, subject to the most extreme temperature swings and evaporation. Only the hardiest species survive there. Lower pools, covered and uncovered more frequently, are richer and more diverse, with conditions closer to the open ocean for more hours of each day. When the tide returns, and the fresh seawater floods back into the pool, the transformation is almost immediate. Fish emerge from hiding. Anemones extend. The whole community rouses itself and begins to move. The tide pool is like a little engine that restarts twice a day, fueled by the returning water. Charles Darwin, who was a meticulous observer of natural environments throughout his voyages, wrote about the tide pools of South America and the Galapagos with evident delight. He spent hours crouched over them, cataloging species, watching behavior, thinking about the adaptations he was seeing. The pressures of the tidal zone, he understood, were among the strongest selective forces that life encountered. The creatures of the tide pool were among the most thoroughly shaped by their environment of anything he had observed. Tide pools continue to be valuable scientific environments today. They are like natural laboratories, small, visible, bounded, and responding to a regular experimental intervention twice a day when the tide changes the conditions. They are among the most studied ecosystems in marine biology, and yet they continue to yield surprises. Tidal power is one of the oldest and most reliable forms of renewable energy ever used by humans. Long before there was any scientific understanding of what caused the tides, people living along tidal coastlines recognized that the tide's movement was a source of power. The water that surged twice a day was regular, reliable, and strong enough to turn a mill wheel. And so tidal mills were built, small mills, positioned so that the incoming tide filled a mill pond, and as the tide retreated, the water was allowed to flow back out through a controlled channel where it turned a wheel that ground grain. Tidal mills have an ancient history. There are references to them in Ireland from around the 7th century of the Common Era, and archaeological evidence of tidal mill structures in England, France, and the Netherlands from around the same period. A remarkably well-preserved tidal mill at Nendrum Monastery on an island in Strangford Lough in Northern Ireland has been dated to around 619 of the Common Era, making it one of the oldest surviving examples of tidal power infrastructure in the world. The Ealing Tide Mill in Hampshire, England, dates to around the 11th century and is still operational today. It grinds flour commercially, using the same basic principle as the original medieval mill, with the tide filling the mill pond and the receding water turning the wheel. It is one of the only working tidal mills in the world and offers a direct, unbroken line of connection between modern renewable energy and medieval water power. The modern version of tidal power is more sophisticated but operates on related principles. Tidal barrages, essentially large dams built across tidal estuaries, allow water to flow through turbines as the tide rises and falls, generating electricity. The Lorance Tidal Power Station in Brittany, France, opened in 1966 and was, for decades, the largest tidal power installation in the world. It still operates and still generates a significant amount of electricity from the tides of the English Channel. More recent developments use tidal stream generators, underwater turbines placed in the path of tidal currents, operating much like wind turbines, except driven by moving water rather than moving air. Tidal currents, particularly in narrow channels where water is funneled and accelerated, can generate substantial and extremely reliable energy. Unlike solar power, which disappears at night and varies with cloud cover, and unlike wind power, which is intermittent, tidal power operates on a schedule that is known to within minutes, decades in advance. Because the tides are driven by the perfectly predictable gravitational forces of the moon and the Sunday. The ancient monks grinding grain on the shores of Strangford Lough, and the engineers designing modern tidal stream turbines for the waters around Scotland and Nova Scotia are connected by the same basic insight that the tide is free energy, delivered twice a day, without fail, because of the moon. We just need to find better ways to catch it. The tides move enormous amounts of sediment and shape entire landscapes over geological time. Water is a medium that moves things. Sand, silt, clay, gravel, all of it can be carried by water in motion, deposited when the motion slows, picked up again when the motion accelerates. And tidal water, moving in and out twice a day, is extraordinarily effective at this work of transport and deposition. The tidal flats that fringe many coastlines are built almost entirely from tidal sediment transport. The Wadden Sea, a vast, shallow tidal area along the coasts of the Netherlands, Germany, and Denmark, is one of the largest intertidal systems in the world. It consists of thousands of square kilometers of tidal flats, salt marshes, tidal channels, and islands, an entire landscape created and maintained by the twice-daily movement of tidal water carrying and depositing sediment. The Wadden Sea is now a UNESCO World Heritage Site and one of the most important coastal ecosystems in Europe, home to millions of migratory birds that use its mudflats as a refueling stop on journeys between Arctic breeding grounds and African wintering areas. The history of the Netherlands and the Wadden Sea coastline is also a story of the constant tension between tidal processes and human efforts to control them. The Dutch have been building dikes and reclaiming land from the tidal sea for over 1,000 years, some of the most sophisticated land-water management in human history. The windmills that are now an iconic image of the Netherlands were pumping stations, moving water out of reclaimed tidal land so it could be farmed. The entire country has been in a continuous negotiation with the tide for as long as it has existed as a civilization. In river delta systems where large rivers meet the sea, the interaction between river sediment, tidal forces, and wave energy creates some of the most complex and ecologically valuable landscapes on Earth. The Mississippi Delta, the Ganges-Brahmaputra Delta, the Nile Delta, the Amazon Delta, all of these are formed by the balance between sediment deposited by rivers and sediment sorted and redistributed by tidal and wave energy. They are places of extraordinary ecological richness, and they are also places of extraordinary human density, because their flat, rich soils and abundant fisheries have supported large populations for thousands of years. They are also places of growing vulnerability, as sea levels rise and tidal patterns shift with changing ocean temperatures and ice melt. The relationship between coastlines and tides is not static. It is ongoing, dynamic, and at this point in history, under pressures it has not faced before. Part, end, part, end. The timing of the tide is not perfectly regular, and sailors have always had to understand why. If you expected the tide to be purely mechanical, moon here, tide there, same time every day, you would quickly be surprised by the reality of navigating or working along a coast. The tide is regular, but it is not simple. Its timing and height vary in ways that sailors, fishermen, and coastal engineers must understand with some precision, because the consequences of miscalculation can range from inconvenient to dangerous. The most obvious variation is that high tide does not happen at the same time every day. It happens roughly 50 minutes later each day, because the Moon moves through its orbit as Earth rotates, and Earth has to rotate a little extra to catch up with where the Moon has moved. This means that if high tide was at noon today, it will be at approximately 12:50 tomorrow, and at 1:40 the day after that. Plan your boat launching or your shellfish harvesting by last week's tide table, and you will be wrong by several hours. But the delay of about 50 minutes per day is itself just an average. The actual interval varies depending on where the Moon is in its orbit and where the Sun is positioned. During spring tides and neap tides, the timing shifts in ways that compound the variation, and the geometry of local coastlines introduces additional irregularities. Some harbors have what is called a stand of the tide, a period where the water level barely changes for an extended time, neither rising nor falling, before the movement resumes. This happens when the tidal dynamics of the area temporarily reach an equilibrium, and it can make the apparent tide look almost still for an hour or more before it begins to fall or rise again. The establishment of the port, the time of high tide, at a given location relative to the position of the Moon, is a figure that mariners historically memorized or recorded for every harbor they used. Each port has its own establishment, its own particular relationship between the Moon's position in the sky and the actual timing of high water. The establishment of the Port of London, for example, is approximately 3 hours after the Moon crosses the meridian. High tide in the Thames follows the Moon overhead by about 3 hours. This figure was known and used by Thames bargemen for centuries, before anyone understood why it was what it was. The ability to predict tides accurately was genuinely valuable, not just as a matter of commerce and navigation, but sometimes as a matter of military strategy. The planning of the D-Day landings at Normandy in the Second World War involved careful analysis of tidal conditions. The assault required low tide at a specific time before dawn, so that the beach obstacles planted by German engineers would be exposed and visible before the landing craft reached them. The tidal conditions that met those requirements occurred only on a few days in early June. When bad weather forced a delay, the planning officers had to weigh the deteriorating conditions against the narrow tidal window remaining. The tides of the English Channel were not an afterthought to the largest military operation in history. They were one of its central constraints. Scientists can predict tides with extraordinary precision many years into the future. One of the remarkable things about tides is that, because they are driven by the gravitational forces of the Moon and the Sun, forces that can be calculated with exquisite precision using celestial mechanics, tidal predictions can be made far in advance with a level of accuracy that is genuinely impressive. The mathematics of tide prediction developed through the 19th century in a process driven by both practical and scientific needs. The British Admiralty, responsible for navigating the Royal Navy and the enormous merchant fleets of the British Empire through every significant port in the world, had a deep interest in accurate tide tables. The mathematician and physicist William Thomson, better known as Lord Kelvin, developed a tide predicting machine in 1872 that used a system of gears and pulleys to physically compute the superposition of multiple tidal components, producing tide predictions by mechanical analog computation. This machine, and the improved versions that followed it, could calculate years of tide tables in hours, far faster than human computation. They were in use at major hydrographic offices around the world until electronic computers replaced them in the mid-20th century. Today, tide prediction is done with software that computes the same basic mathematics far faster and with far greater precision. The major tidal prediction programs use dozens of tidal constituents, the individual frequency components of the tide. each corresponding to a particular astronomical cycle, and sum them together to produce predictions that can be accurate to within a few centimeters. The National Oceanic and Atmospheric Administration in the United States publishes tide tables for hundreds of U.S. coastal stations, and similar agencies around the world do the same for their coastlines. For major ports, these predictions are published years in advance and are accurate enough to be used for planning major engineering projects, scheduling dredging operations, and determining safe navigation windows for large vessels. There is something deeply satisfying about this accuracy. The tides arise from astronomy, from the positions and motions of bodies in space, and so they are as predictable as the orbit of the moon itself. In a world full of uncertainty, the tide table is one of the few things that can be trusted to tell you exactly what will happen at a specific place and time years from now. The world's oceans are all connected, and the tide moves through them like a wave around the globe. The ocean is not a collection of separate bodies of water. It is one continuous ocean, divided by continents into basins that are connected by channels, passages, and the open waters of the Southern Ocean. And the tide is not a local event that happens independently in each place. It is a global wave, a slow, enormous pulse that travels around the world in a pattern driven by the astronomical forces. Oceanographers describe the global tide in terms of amphidromic systems, patterns of tidal rotation centered on amphidromic points, where the tidal range is essentially zero, surrounded by tidal waves that rotate around them. Imagine a large circular basin of water that you spin at a particular frequency. The water sloshes around the rim of the basin in a rotating wave, while the center barely moves. The global ocean has a dozen or so such systems, each one an enormous rotating tidal wave centered on an amphidromic point, each occupying a portion of an ocean basin. In the Atlantic Ocean, for example, there are two main amphidromic systems, one in the North Atlantic and one in the South Atlantic. High tide rotates counterclockwise around the North Atlantic amphidromic point, and as it moves, it creates the sequence of high tides that you observe along the European and North American coastlines. The timing of high tide along the coast of Portugal is related to the timing of high tide along the coast of Norway, which is related to the timing along the coast of Newfoundland, all of them parts of the same enormous rotating wave. Understanding this global picture required the development of sophisticated oceanographic models that could account for the shape of ocean basins, the depth of the water at every point, the rotation of the Earth, and the astronomical forcing functions. These models are now extremely accurate and are used not just for tide prediction, but for understanding ocean circulation more broadly, including the patterns of deep water movement that help regulate global climate. The tide connects everything. It is a thread woven through every ocean on Earth, shaped by every coastline, running in every direction at once, driven by the sky. The deep ocean floor moves with the tides in ways most people never think about. We tend to picture the tides as something that happens at the surface, the water rising up a beach, surging into a harbor, flooding across a tidal flat. And that is indeed where the tides are most visible and most obviously felt. But the tidal forces that move the ocean do not stop at the surface. They reach all the way down to the deepest parts of the sea, and the effects of tides at the bottom of the ocean are strange and surprising, and far less understood than the tides we see at the shore. In the deep ocean, in those vast, flat, abyssal plains that lie 4 or 5 kilometers below the surface, the tide still moves the water. The pressure changes with the tide, subtly but measurably. The current at the bottom of the deep sea shifts and surges with the tidal rhythm, and in some places these deep tidal currents are strong enough to transport sediment and sculpt the landscape of the seafloor in ways that oceanographers are still actively studying. But the most interesting deep ocean tidal phenomenon involves what happens when tidal currents in the deep sea encounter underwater topography, seamounts, ridges, the steep walls of continental shelves. When a horizontal tidal current hits a vertical obstacle in the deep ocean, it can generate internal waves, waves that travel not on the surface of the water, but deep within the ocean, along the boundaries between water layers of different temperature and density. These internal tidal waves are enormous. They can be hundreds of meters tall waves moving through the interior of the ocean, invisible from above, unstoppable, and largely undetectable without specialized instruments. Where they propagate into shallower water, they can interact with the ocean floor in ways that mix deep, cold, nutrient-rich water up toward the surface. This mixing is not just a curiosity, it is a fundamental part of the ocean's circulation system, redistributing heat and nutrients across the planet. Some of the most important mixing in the global ocean, the kind of deep, turbulent mixing that helps drive ocean circulation and regulate the climate, is powered in part by these internal tidal waves. Tides that began as gravitational forces from the moon and the sun, that moved the surface ocean, that generated currents in the deep sea, that hit an underwater ridge and transformed into deep internal waves. Those waves eventually break against rough, seafloor topography and mix the ocean's layers. The tide, in this way, is a heat pump and a nutrient pump, and a part of the climate machinery of the whole planet. The ocean is not a simple bowl of water. It is a three-dimensional, layered, constantly moving environment, and the tides animate every layer of it in ways that are still being discovered. There are ancient tide gauges hidden in the landscape that scientists use to read the history of sea levels. Before there were scientific instruments to measure sea level, before there were tide gauges and satellite altimeters, the coastlines themselves were keeping records. Rock surfaces at the sea's edge, marked by the slow work of waves and tidal exposure, preserve information about where the waterline was in centuries past. Underwater ruins of ancient harbors and settlements show where land has subsided or where sea levels have risen. Pollen, preserved in ancient salt marsh sediments, records how those marshes grew and shifted in response to changing sea levels over millennia. The science of reading these ancient sea level records is called paleoceanography, and it has become increasingly important as we try to understand the relationship between past climate and past sea levels, and what that relationship might tell us about the future. What we know from these records is that sea level has varied dramatically over the Earth's history. During the last ice age, which reached its maximum extent roughly 21,000 years ago, so much of the world's water was locked up in continental ice sheets that global sea level was approximately 120 meters lower than it is today. The coastlines of the world looked entirely different. Britain was not an island. It was connected to continental Europe by a vast flat plain, now underwater, called Doggerland, through which rivers flowed and where people lived and hunted for thousands of years. The Persian Gulf was largely dry land. Indonesia was not a chain of islands, but a peninsula extending from mainland Southeast Asia. As the Ice Age ended and the ice sheets melted, sea levels rose dramatically and rapidly by geological standards. This was not a smooth, gradual process. There were episodes of rapid sea level rise, so-called meltwater pulses, when large sections of the ice sheets collapsed into the ocean and sea levels rose by meters over periods of centuries or even decades. These rapid rises reshaped coastlines, flooded valleys and plains, and created new islands where there had been hills. Human populations that had lived on those coastal plains for generations were displaced and had to migrate inland. There is archaeological and geological evidence suggesting that some of the most dramatic episodes of coastal flooding happened within the period of human cultural memory and may have left traces in the flood myths and stories of coastal and riverine peoples around the world. The Black Sea, for example, was likely transformed from a freshwater lake to a saltwater sea in a relatively sudden flooding event as Mediterranean water broke through the natural dam at the Bosphorus, an event that some researchers have connected to the story of Noah's flood and similar flood narratives in other traditions. Whether or not that specific connection is accurate, the basic dynamic is real. The rising sea level of the post-siege world genuinely did flood coastal and low-lying landscapes that had been inhabited. The tides continued through all of this, rising and falling against coastlines that were themselves rising and falling over geological and climatic timescales. The tide is constant, but the shore it visits is always changing. Certain animals use the tides as a calendar, synchronizing their reproduction to tidal cycles. The biological clocks we discussed earlier, the internal rhythm that intertidal creatures maintain, even when removed from the tidal environment, are not just for daily activity patterns. Some species use the tidal cycle for one of the most important activities in their lives: reproduction. The California grunion is one of the most famous examples and one of the most dramatic. Grunion are small silvery fish, about 15 centimeters long, that live in the coastal waters of Southern California and Baja California. Several times a year, on the 3 or 4 nights following a full moon or new moon from March through August, the highest spring tides bring grunion to the beach in enormous numbers. The females ride the waves onto the sand and bury themselves tail first in the wet beach, depositing their eggs in the sand just above the waterline. Males follow and fertilize the eggs, then the adults retreat back into the sea with the receding waves. The eggs are now buried in the dry beach above the tide line, high enough that they will not be swept away by the daily tides, but low enough that they will be reached by the next spring tide, which will come in approximately 2 weeks. When those waves wash over the sand and the eggs, the agitation of the water stimulates the eggs to hatch, and the larvae emerge directly into the surf and are carried back out to sea. The timing of this is extraordinary. The grunion are not just responding to the moon or the tides in a general way. They are timing their spawning to a very specific window, the period just after the highest tide of the spring tide cycle, when the tide line will not reach the eggs again for about 2 weeks. This gives the eggs the maximum possible time to develop before they need to hatch. The behavior is calibrated to the rhythms of the moon and the tidal cycle, with a precision that takes years of observation to fully appreciate. The horseshoe crab of the North American Atlantic coast has a similar story. Though it involves creatures that are not true crabs at all, they are more closely related to spiders and scorpions, and have lived on Earth almost unchanged for roughly 450 million years. On certain spring nights in May and June, when spring tides bring the highest water levels of the year onto the beaches of Delaware Bay and other mid-Atlantic bays, horseshoe crabs emerge from the sea in enormous numbers. Females come to lay eggs in the sand above the tide line. Males cluster around them to fertilize the eggs. The eggs of horseshoe crabs are a critical food source for several species of migratory shorebirds, including the red knot, a small sandpiper that migrates from the southernmost tip of South America all the way to the Arctic to breed, stopping at Delaware Bay for roughly 2 weeks in May to refuel. The timing of the red knot's migration, refined over millions of years of evolution, is synchronized with the timing of the horseshoe crab spawn, which is synchronized with the spring tides, which are synchronized with the alignment of the moon and the Sunday. The whole system is a chain of timing dependencies linked ultimately to the gravitational dance of celestial bodies. When horseshoe crab populations decline, as they have in recent decades due to overharvesting for biomedical use and bait, the red knot loses its critical refueling stop, and its populations decline too. The chain of dependencies that evolved over millions of years to take advantage of the tidal calendar is also a chain of vulnerabilities when any part of it breaks. The tide creates an extraordinary optical phenomenon called tidal bores in the air as well as the water. Here is something that exists only in a handful of places in the world and is almost unknown outside of them. In tidal rivers with particularly dramatic bores and certain atmospheric conditions, the tidal bore can be preceded by a visible wave of mist, a low, rolling cloud bank pushed ahead of the oncoming water by the displaced air. As the bore roars upriver, it pushes the air in front of it, and in the right conditions, usually cool mornings with a bit of moisture in the air, that displaced air cools and condenses into fog, creating a ghostly pale wave, rolling silently ahead of the water itself. Local communities along rivers with significant tidal bores have observed and named these phenomena for generations. On the Qiantang River in China, the mist preceding the bore has been described in classical poetry and landscape paintings going back more than 1,000 years. It arrives in the pre-dawn stillness, grey and quiet, before the thunder of the water itself, as though the river is announcing itself with a whisper before the shout. There is also a strange quality to the sound environment just before a large tidal bore arrives. The bore pushes a pressure wave ahead of it in the water, an underwater sound wave, a deep thrum that can sometimes be felt in the chest or in the feet before the bore itself rounds a bend and comes into view. People who have spent time near tidal bores describe the experience of waiting for one as having its own particular character, the odd stillness, the sense that the river has paused and pulled back its breath before something large happens. These sensory experiences, the mist, the deep sound, the stillness, the roar of the arriving water, are part of why tidal bores have fascinated and sometimes frightened people throughout recorded history. They do not behave the way water is supposed to behave. They run upstream. They announce themselves with noise and mist. They transform a river in minutes from something quiet and familiar into something churning and strange. And then they are gone. And the river recovers. And the twice-daily waiting begins again. The moon's influence on tides has measurably slowed the rotation of the Earth over billions of years. We touched on this briefly when discussing how the moon is moving away from Earth, but it is worth dwelling on the full scale of it, because the numbers are extraordinary. Earth today completes one rotation one day in approximately 23 hours, 56 minutes, and 4 seconds. That is the length of what scientists call the sidereal day, the time it takes for the Earth to rotate once relative to the distant stars. The solar day, the time from one noon to the next, is slightly longer because the Earth is also moving around the Sun. But the difference is small. 4.5 billion years ago, when Earth was newly formed and the Moon had just been created, most likely by a giant impact between the early Earth and a large body roughly the size of Mars, the Earth was spinning much faster. The early Earth completed one rotation in perhaps just 5 or 6 hours. A day on the newborn Earth was not a day we would recognize. The sky would have wheeled overhead with dizzying speed. Since then, the tidal friction, the interaction between the tidal bulge that the Moon raises in Earth's oceans and solid body, and the gravity that drags on that bulge, has been transferring rotational energy from Earth to the Moon. Earth has been slowing down, and the Moon has been getting pushed into a higher, wider orbit as it receives that transferred energy. The rate of slowing is approximately 2 milliseconds per century. 2 milliseconds per century sounds like nothing. But over 4.5 billion years, those 2 milliseconds per century add up to a slowing of somewhere in the neighborhood of 18 hours. Earth's day was once 6 hours long. Now it is 24. The tidal friction, working patiently across geological time, has stretched Earth's day by 18 hours. This has consequences that ripple through the history of life. When Earth rotated faster, the Coriolis effect, the tendency of moving air and water to curve because of Earth's rotation, was stronger, affecting weather patterns. The tidal ranges in the young Earth's ocean were dramatically larger, creating more intense intertidal mixing. The geological and atmospheric effects of a faster spinning world were deeply different from those of the world we live in today. One of the ways scientists know how fast the Earth was spinning in the deep past is by reading tidal rhythmites, those layered ancient sedimentary deposits we discussed earlier. Each layer represents a tidal cycle. By counting layers and comparing them to the patterns of spring and neap tides, researchers can work out how many tidal cycles occurred per year, and from that, how many days were in a year, and from that, how long a day was. The results have confirmed the picture drawn by orbital mechanics. Earth has been spinning slower and slower, and the tides have been the mechanism. Every tide that rises is doing an infinitesimally tiny amount of work on the Earth-Moon system. Every tide is slowing Earth down by a fraction that cannot be measured, and pushing the Moon outward by a fraction that cannot be measured. But nature has infinite patience, and what cannot be measured in any single tide has been measured across billions of tides, accumulated into a result that has transformed the world. The tides of Antarctica play a significant role in global ocean circulation and climate. Antarctica is a continent, but it is surrounded by ocean, and the Southern Ocean that rings it is one of the most important parts of the global climate system. Here, some of the coldest, densest water on Earth forms and sinks to the deep ocean floor, beginning a global journey that eventually connects every ocean basin. This process, called deep water formation or thermohaline circulation, is partly driven by the tidal mixing that occurs in the Southern Ocean and around the margins of Antarctica. The continent of Antarctica is also partly floating not the land itself, but the ice shelves that extend from it over the ocean. These enormous slabs of ice, some of them the size of France, are grounded at their inland edges and floating at their seaward edges, where they extend out over the water. And because they are floating, they respond to the tides. Antarctic ice shelves flex with the tides. The tidal signal has been measured directly in the movement of the ice surface. The shelves rise and fall by a meter or more with the passing tides. This flexing is concentrated at the grounding line, the boundary between the ice that is resting on the seafloor and the ice that is floating. This boundary is critically important because it is where the ocean can get underneath the ice shelf and melt it from below. Tidal action near ice shelf, grounding lines, pumps relatively warm ocean water in and out from beneath the ice with each tidal cycle. This pumping accelerates the melting of the ice shelves from below. In some locations, scientists have observed that ice shelf melt rates are significantly higher during spring tides than during neap tides, because the greater tidal motion drives more exchange of water beneath the shelf. As climate change warms the Southern Ocean and threatens the stability of Antarctic ice shelves, understanding the role of tides in ice shelf dynamics has become increasingly urgent. The tidal processes happening in places that most humans will never see or visit are directly connected to the question of how quickly Antarctic ice will melt and how much global sea level will rise as a result. The tide, in its patient twice-daily motion, is one of the forces shaping the future of every coastline on Earth. Humans have been studying the tides for as long as they have been keeping written records, and probably much longer. There is a fragment of clay tablet from ancient Babylon, dating to around 420 years before the Common Era, that contains what appears to be a record of observations of the tidal flooding of the Euphrates Delta at the Persian Gulf. The Babylonians were extraordinary astronomers and careful observers of natural phenomena, and the fact that someone was recording tidal observations on clay tablets in ancient Iraq around 400 years before the Common Era tells us something important. People have always understood that the tide mattered, and that understanding it required careful, patient observation. The ancient Chinese were also early and careful tidal observers. The Qiantang River bore, which we discussed earlier, was observed and recorded in official chronicles from the Han Dynasty around 2,000 years ago, and tidal tables for ports along the Chinese coast were being compiled and used for navigation by at least the 9th century of the Common Era. Chinese maritime traders and fishermen depended on accurate knowledge of tidal patterns in the complex, shallow, island-dotted waters of the South China Sea and the East China Sea, and they developed practical tidal prediction methods through careful empirical observation long before any formal scientific theory of tides existed. In the Islamic world of the 9th through 11th centuries, scholars who were synthesizing and extending the knowledge of Greek, Persian, and Indian science also wrote about tidal phenomena. Al-Biruni, writing in the early 11th century, produced thoughtful observations about tides and their relationship to the moon, and his work was part of a broader tradition of careful natural philosophy that helped transmit and preserve this knowledge through the medieval period. The Viking navigators of the North Sea and the North Atlantic, operating in some of the most tidally active waters in the world, had sophisticated practical knowledge of tidal patterns that they used in their voyages along the coasts of Europe and across to Iceland and Greenland. The Norse sagas contain references to tidal conditions that suggest their mariners had a detailed working knowledge of tidal timing and range, even if they did not have a formal theory of what caused it. The study of tides is, in miniature, a history of human curiosity about the natural world. It involves practical knowledge driven by survival and commerce, careful observation accumulating over generations, theoretical advances when the right mathematical tools became available, and eventually a modern understanding that connects the local tide you see at a beach to the gravitational forces of bodies in space and the deep history of the solar system. The tide interacts with the light of the moon in a way that coastal peoples have always found meaningful. There is a particular kind of night that coastal people know well, a full moon night with a spring tide, when the highest high tide of the month arrives at the same time that the full moon is riding low over the water. These nights have a quality that is hard to describe to someone who has not experienced them. The water reflects the moonlight across a vast expanse of flat, wet sand, or across the calm, open water of a bay, and the light seems to come from below as much as above, doubling itself in the mirror of the sea. Traditional fishing communities around the world planned certain activities specifically for these moonlit high tides. In some tropical regions, certain reef fish spawn on predictably scheduled nights, tied to the lunar cycle and the associated tidal conditions, and fishermen who knew the pattern could position themselves at the right place at the right time, in water illuminated by a full moon, to take advantage of the aggregating fish. This knowledge, developed over generations through patient observation, was sometimes treated as proprietary, shared only within families or guilds, kept secret from rival fishing communities. In the British Isles, the combination of a full moon and a spring tide on certain autumn nights created what fishermen called the harvest moon tide, named for the same harvest moon that allowed farmers to work their fields into the night. The large full moon of early autumn that rises shortly after sunset and stays low and orange on the horizon. During these tides, particularly on the estuaries and tidal rivers, salmon would run on the high water, and nets set at the peak of the spring tide on a harvest moon night could take catches that would not be seen again for weeks. The relationship between the tide, the moon's light, and the behavior of marine life is not just practical law. It is also genuinely scientific. Many marine organisms respond to moonlight directly, using it as a cue for feeding, migration, and reproduction. Coral spawning, one of the most dramatic events in the marine world, is triggered by the combination of water temperature, lunar phase, and tidal conditions. Millions of coral polyps across an entire reef releasing their eggs and sperm simultaneously, filling the water with pale pink drifting bundles on certain nights in late summer. The moonlit ocean is a chemically and biologically different place from the moonless ocean, and the tide helps orchestrate the timing of this difference. To stand at the edge of the sea on a full moon night, with a spring tide running and the moonlight laying itself flat across the water, is to be present for something very old. The moon is pulling the water toward it, as it always has. The water is rising, and the beach is disappearing behind you, as it always does. And somewhere in the illuminated shallows, creatures are responding to signals tidal, lunar, thermal that have been calling to them for millions of years. The tide has a sound that changes with each stage of its cycle, and experienced coastal people can hear what the tide is doing. This is a piece of knowledge that belongs primarily to people who have spent years working on or near the water, and it is the kind of knowledge that does not appear in scientific papers very often, but is genuinely real and genuinely interesting. The sound of the sea is not constant. It changes as the tide changes, and those who know how to listen can often tell, without looking, approximately where the tide is in its cycle. At low tide, on a beach with exposed rocks and rock pools, the sound tends to be sharper and more complex. Waves break over and around rocks, producing a layered, irregular sound of water moving over hard surfaces. The click and tumble of small stones in the wash, the hollow knock of water entering a sea cave or a crevice. The sound carries differently over exposed wet rock than it does over water. As the tide begins to rise and the rocks submerge, the character of the sound changes. The sharp, complex sounds smooth out as the hard obstacles disappear beneath the water. The waves begin to break on sand rather than rock, producing a deeper, softer collapse. The water running back down the beach has a continuous hissing sound over sand that is different from the rattling of retreating water over stone. At full high tide, on a gently sloping beach, the waves may break far up the sand in long, exhausted surges, reaching their furthest point with a kind of final sigh before pulling back. The sound can be slower and more measured, each wave traveling further and dying more completely than it would at low tide, with its energy spread over more shallow water. Experienced sailors and fishermen who spent long periods living on boats in tidal waters developed a detailed auditory knowledge of tidal states. On foggy nights, or in darkness, when visual cues were absent, the sound of the water against a hull or a pier or a breakwater told them things about the current state of the tide and the resulting set and drift of the water that affected their navigation and their safety. The sea has a voice that changes with the tide, and like most voices, it rewards those who spend time learning to listen to it. Tides affect the frequency of earthquakes in certain geological settings. This one is perhaps the most surprising scientific fact about tides. Surprising because it connects two things that seem like they have nothing to do with each other: the gentle, rhythmic rising and falling of the ocean, and the sudden violent release of energy in the rock deep below the surface. The connection is real and has been documented by seismologists with data from regions around the world. In some geological settings, particularly where there are active fault systems close to coastlines, or where tidal loading and unloading is significant, the regular stress changes caused by the changing weight of tidal water can subtly influence the timing and possibly the frequency of small earthquakes. The mechanism works like this. Faults in the Earth's crust are under stress, the accumulated strain of geological forces pushing and pulling on the rock. Many faults are close to the threshold of failure, close to the point where they would slip and generate an earthquake. A small additional stress, added at just the right time, can be the increment that tips a fault from nearly failing to actually failing. The tidal loading of the sea floor, the extra weight of water at high tide pushing down on the crust, changes the stress conditions in nearby fault systems. In some orientations and locations, high tide increases the stress on certain fault planes and decreases it on others, depending on the geometry. Careful statistical analysis of earthquake catalogues in tidally active regions has shown that in some areas, there is a statistically significant tendency for small earthquakes to occur at particular phases of the tidal cycle. This relationship is not strong enough to be useful for earthquake prediction. The additional tidal stress is tiny compared to the total stresses involved in large earthquakes, and most tidal maxima do not trigger earthquakes. But it is a beautiful example of the interconnectedness of Earth systems. The ocean and the lithosphere, the solid rock of Earth's crust, are not isolated from each other. They interact through the weight of the water, through the loading and unloading of the tidal cycle, through geological time, and through individual tidal cycles. The tide reaches down not just to the seafloor, but into the rock beneath, nudging the stress state of faults, adding its infinitesimal increment to the accumulated tension of the geological world. The speed at which tidal waves travel across the deep ocean is extraordinarily fast. The tidal wave, using that term in the proper technical sense, meaning the wave-like rise and fall of the ocean tide, not the tsunamis that are sometimes incorrectly called tidal waves, travels across the open ocean at speeds that are hard to believe until you do the calculation. The speed at which a wave travels through water depends on the depth of the water. In very deep water, waves travel faster. In shallower water, they slow down. For the tidal wave, which has a wavelength equal to half the circumference of the Earth, about 20,000 kilometers, the relevant depth is the average depth of the ocean, about 3,800 meters. At that depth, the tidal wave travels at approximately 700 kilometers per hour. That is roughly the cruising speed of a commercial jet aircraft. This is why the tide is coordinated over vast distances. The tidal forcing from the moon creates a response in the ocean that propagates at this extraordinary speed, allowing the tidal signal to travel from one side of an ocean basin to the other in a matter of hours. The Atlantic Ocean is approximately 6,000 kilometers wide. At mid-latitudes, the tidal wave could cross it in about 8 or 9 hours. In practice, the actual tidal propagation is more complex because of reflections from coastlines, interference between different tidal waves, and the effects of ocean topography, slowing the wave in shallower regions. But the basic speed of tidal propagation is genuinely remarkable. The ocean responds to the moon at speeds that would seem more appropriate to air travel than to water movement. There is a place in the ocean with no tidal range at all, the amphidromic point. We touched on amphidromic systems earlier, but the amphidromic point itself deserves its own moment of attention because it is one of the more elegant and counterintuitive concepts in tidal science. An amphidromic point is a location in the ocean where the tidal range is, in theory, exactly zero. The tide does not rise and fall there. While the surrounding ocean experiences the full drama of its tidal cycle, high tides and low tides, spring tides and neap tides, the amphidromic point itself sits perfectly still, the eye of the tidal storm. Around the amphidromic point, the tidal wave rotates. High tide spins around the central still point like a wave pattern in a bowl of water that has been set spinning. The high tide crest moves in a circle around the amphidromic point, and the tidal range increases with distance from the center. The farther you are from the amphidromic point, the larger the tidal range you experience. There are about 12 major amphidromic points in the world's oceans, and several smaller ones. They are not evenly distributed. Their positions are determined by the shape of ocean basins and the way tidal waves interact and interfere. There is one in the middle of the North Sea that governs the tidal behavior of the surrounding coastlines of Britain, France, Belgium, the Netherlands, Germany, and Denmark. There is one in the equatorial Pacific. There is one in the South Atlantic. The existence of amphidromic points was predicted mathematically long before it was confirmed observationally, because directly measuring the tide at a specific point in the middle of the ocean is not easy. But the development of satellite altimetry, the ability to measure sea surface height from space with sufficient precision to detect the tidal rise and fall, confirmed the location and behavior of amphidromic points in the coin message, 1970s and 80s. There is something almost meditative about the concept of the amphidromic point, a place of perfect stillness at the center of a system of constant motion, the tidal energy rotating endlessly around it while it itself remains at rest. The tide, which we experience as a rising and falling, a coming and going, reveals itself at the amphidromic point to be a rotation, a circular motion that only appears as a rise and fall when you observe it from the edge of the system, from the shore. The sound of the tide is one of the oldest sounds a human being can hear. This is not a scientific fact in the way most of the others in this conversation have been, but it feels worth saying quietly, here near the end of this exploration, as the tide of sleep begins to come in for you. The sound of the ocean, of waves moving across the shore, of water surging and retreating over rock and sand. This sound predates humanity. Our ancestors heard it. Their ancestors heard it. Going back hundreds of thousands of years, through ice ages and warm periods, across migrations and adaptations, and long stretches of time that we can hardly conceive of, the ocean was somewhere nearby, making its sounds, moving with its tides. There is a reason that the sound of ocean waves is one of the most reliably relaxing sounds that most people know. There is a reason it appears on white noise machines and sleep aids and relaxation recordings. Some researchers have suggested that the brain processes certain low-frequency, rhythmically variable sounds like ocean waves as inherently non-threatening, as signals that the environment is calm and nothing alarming is happening. The pattern recognition parts of the brain that are always listening for sudden sounds, for sharp noises that might signal danger, can relax into the steady rhythm of the waves, because the waves are predictable, not threatening, and very old. The tide itself, the slow rise and fall of the water, the long-period breathing of the ocean, is too slow and too vast to be heard as a sound in the conventional sense. You do not hear the tide the way you hear a wave, but you see it. You feel it in the changing texture of the sand beneath your feet, in the slow migration of the waterline toward you or away. You sense it in the way the smell of the sea changes as the tide exposes more wet sand and rock. And if you lie near the ocean on a still night and let your breath slow to match the rhythm of the waves, you might find that the two rhythms align more easily than you expected. That there is something in the ocean's pace that is close, in some ways, to the pace of the resting human body. The waves come and go. Your breath comes and goes. The tide advances and retreats. Your attention advances and retreats. It is one of those correspondences that is probably coincidence and probably meaningful at the same time. The tide is also a reminder that the world runs on timescales far beyond our own. The tides we see at the beach today are different in measurable ways from the tides that shaped the coastlines of the last ice age. The tides of 1 billion years from now will be different from the tides of today, because the moon will be farther away and Earth's rotation will be slower. And the tides of 1 billion years ago were dramatically different from anything we have experienced. Stronger, faster, more extreme, shaping a world in which the continents were in different positions and the ocean basins had different shapes. We are living in a particular moment in the long story of Earth's tidal history. The moon is at a particular distance. Earth is spinning at a particular speed. The ocean basins have a particular shape that produces the tidal patterns we see. All of this is contingent on where we are in a timeline, stretching billions of years in both directions. There is something both humbling and deeply calming about this perspective. We tend, understandably, to think of the world we live in as the world as if the current arrangement of continents, the current length of the day, the current distance of the moon, The current tidal patterns were fixed and permanent, but they are not. They are a moment, a single frame in a very long film. And within our lifetimes, within any individual human lifetime, the tides will not change in any way that is noticeable. The same tide that came in this morning will come in again tomorrow and the day after and every day, for as long as any of us will live to see it. It is a point of profound continuity in a world where almost everything else changes. Civilizations rise and fall and the tide continues. Languages are born and forgotten and the tide continues. The faces of the mountains erode and the tide continues. There is something offered by that continuity, not an argument that nothing matters, but a quiet reminder that some things are very, very stable. That beneath all the change and urgency and noise of human life, there are rhythms so old and so persistent that they put everything else in a kind of proportion. The tide has been coming in for 4 billion years. It is coming in right now, somewhere on every coastline on the planet, even as you read this. It will come in again tonight, and again tomorrow morning, and again, for longer than any of us can imagine. That kind of permanence is, in its way, one of the most restful things to contemplate. There is one more small thing worth knowing before we let the tide carry us away from this conversation. Even within a single tide cycle, the quality of the water changes in ways that experienced coastal people have always noticed. As the tide floods in, it brings cooler, clearer water from the open sea, flushing out the warmer, murkier water that has been sitting in shallows and estuaries since the last high tide. The incoming tide often brings with it a distinct smell, cleaner, crisper, carrying traces of the open ocean, of distance and depth. The receding tide carries away whatever the sea has deposited, the fresh cast of seaweed, the tumbled shells, the small debris of coastal life. Fishermen and divers have long known that water clarity and temperature change significantly with the tidal state, and that certain fish and marine creatures respond to these changes in predictable ways. Some species feed aggressively on the first hour of the incoming tide, when fresh, well-oxygenated water brings prey items tumbling into new positions. Others are most active on the outgoing tide, following the water off the flats and into channels where the concentrating effect of the retreating water makes prey easier to find. The tide, in this way, is not just a mechanical change in water level. It is a change in water character, in temperature, clarity, salinity, oxygen content, and the distribution of nutrients and prey. The whole coastal food web is tuned to these changes, layered on top of the daily light cycle and the seasonal cycle in a complex three-dimensional rhythm that the most expert naturalists spend lifetimes studying and still find endlessly surprising. There are places in the world where the interaction of tidal mixing and nutrient delivery creates conditions for extraordinary biological abundance. The cold, nutrient-rich waters of the Newfoundland Grand Banks, where the Labrador Current and the Gulf Stream interact in a zone of intense tidal and oceanographic mixing, produced fish stocks so enormous that early European explorers reported being able to dip baskets into the sea and pull them out full of cod. The extraordinary marine abundance of the Pacific Northwest coast of North America, with its massive salmon runs and its vast kelp forests and its orca and humpback whale populations, is sustained in significant part by tidal mixing that delivers nutrients from the deep ocean into the productive surface layer where sunlight can drive photosynthesis. These are places where the tide has been building marine abundance for thousands of years, and where human communities built their entire cultures around that abundance. The tide gives, and the tide takes away. It covers and reveals. It delivers and removes. It is one of the fundamental metabolic processes of the ocean, and through the ocean, of the living world. One last thought, and then we rest. Wherever you are right now, you are not very far, in the grand scheme of things, from water that is being moved by the tide. If you are on a coastline, the tide may be arriving at this very moment, or it may be near its peak, or it may be quietly retreating back toward the open sea. If you are inland, the rivers that run near you likely feel the tidal influence somewhere along their length, where fresh water meets the ocean, and the daily pulse of salt and fresh water mixing creates its own kind of boundary. Even if you are far from any ocean, you are on a planet whose rotation is being slowly shaped by the tides, whose land surface rises and falls by centimeters twice each day, whose relationship with its moon is defined in part by this constant gravitational conversation between water and sky. We are all, in a sense, tidal creatures, living on a tidal world, shaped by tidal forces over billions of years of evolution, held in place by the same moon that raises the water. And tonight, like the water at high tide, we are at rest. There is one more small thing worth knowing before we let the tide carry us away from this conversation. The tide arrives differently, depending on where you are standing. If you are standing on the western coast of a continent, you tend to see the tide from one direction, on the eastern coast from another. In a harbor, at the end of a long, narrow inlet, you might see the tide arrive noticeably later than it does at the open coast a short distance away, because the tidal wave has had to travel up the inlet to reach you. On an exposed headland, the tide might arrive sharp and quickly, the open ocean offering nothing to delay it. Every place has its own tidal personality, shaped by its geography and its orientation to the tidal forces. Every harbor, every cove, every estuary, every beach has a particular way that the tide arrives and departs that is slightly different from every other place. The people who know a coast well enough know these personalities the way you might know the habits of an old friend when the tide tends to peak a little earlier here because of the shape of the bay, when it drains more slowly there because of a particular sandbar configuration, where the current runs fastest on an ebb tide and slowest on a flood. This local, particular, intimate knowledge of tidal behavior was the practical science of coastal people for most of human history. It did not require knowing about the moon's orbital mechanics or the mathematics of amphidromic systems. It required patient observation across seasons and years, comparison of notes between fishermen and sailors, the gradual accumulation of knowledge about one specific place and its water. It was science without the name of science, knowledge without the apparatus of institutions, understanding earned through attention and time. That kind of knowledge is still valued today by the people who work on and near the water. Modern tide tables and GPS and real-time oceanographic data have not entirely replaced the hard-won local understanding that comes from spending decades watching how a particular piece of coast behaves. The data is useful. The local knowledge is irreplaceable. The tide rewards attention. It always has. And so, dear listener, we have reached the end of our journey along the water's edge. We began with the moon, pulling at the ocean from 384,000 kilometers away, patient and invisible, and absolutely reliable. We walked through the science of why the water bulges on both sides of the Earth, through the extraordinary tidal ranges of the Bay of Fundy, through the dramatic bores that roar up rivers in China and Brazil and England. We visited the ancient records of tides preserved in rocks laid down hundreds of millions of years ago, and the ancient cultures that built their lives around the rhythm of the water. We spent time in tide pools, those small, complete worlds where sea stars and anemones and tiny fish live out their days in miniature, subject to the twice-daily transformation of their world. We thought about the tidal heating of Io and the hidden ocean of Europa, and what it means that the same force that gently raises the water level at a beach also keeps entire moons molten or liquid across the solar system. We considered the patient tidal mills turning in the channels of medieval Ireland and England, grinding grain from the same renewable energy source that modern engineers are now designing turbines to capture. We traced the way tidal water builds salt marshes and tidal flats, and how those ecosystems support millions of creatures and buffer coasts from storms. We stood at the edge of the ancient tidal zone, where, hundreds of millions of years ago, the ancestors of every land vertebrate alive today were making their first uncertain steps toward the shore. We learned that the tide moves through the solid rock beneath the ocean, as well as the water above it. That the speed of a tidal wave crossing the open ocean rivals the speed of a jet aircraft. That there are points in the ocean where the tide does not rise or fall at all, perfect centers of stillness around which all the tidal motion rotates. That the grunion and the horseshoe crab and the coral polyp have been reading the tidal calendar with precision that rivals any instrument we have built. We visited the ancient Babylonian clay tablets, where tidal observations were first scratched into the record. We listened for the sound of the boar approaching up a river before dawn, the low rumble felt in the chest before the white line appears on the water. We read the layered sedimentary rock that preserves the rhythm of the tides from 600 million years ago. We thought about the way the tide is connected to the earthquake and the ice shelf, and the migration of a small sandpiper flying from the tip of South America to the Arctic. And we came to the simplest and perhaps most important thing of all, the fact that the tides have been here as long as there has been an ocean, that they have shaped everything from the moon's orbit to the genome of intertidal creatures, and that they will continue long after any particular tide watcher has come and gone. The ocean does not hurry. The tide does not insist. It simply comes and goes, with a patience and reliability that have nothing to do with urgency and everything to do with deep, ancient, cosmic law. As you lie here now, perhaps already drifting, perhaps already at the shoreline between waking and sleep, imagine that you can hear the water, not the noise of surf in a storm, but the quiet sound of a calm shore in the early hours before dawn. The water moving over smooth pebbles, the soft collapse of a small wave onto flat sand, the hiss of water retreating through the spaces between stones. In a few hours, that beach will be changed. The tide will have come in, covered the rocks you can see now, rearranged the sand a little, left behind a fresh tide line of shells and wrack and the small evidence of the sea's overnight visit. And then it will go out again. And this process, this ancient patient exchange between the ocean and the shore, will continue for billions of years to come. You do not need to do anything to participate in that. You are already here. You are already part of a world that has tides and moons and patient forces pulling at the water. Let the tide carry you now. Let the breath come in and go out without your help, the way it always does when you finally stop managing it. Let the thoughts drift in like water and let them drain away again. The tide is coming in. The water is rising. The world is breathing. If some part of you is still awake and would like to continue exploring, there is another gentle journey waiting for you whenever you are ready. But if your eyes are growing heavy, and I hope they are, then close them now. Let the sound of the water fill the space behind your eyes. The ocean has been here for 4 billion years. It knows how to hold you while you sleep. Good night.